Welcome to a lesson with Dr. Powell. In the last video, we discussed setting up some integrals to help us compute the centroid of a thin wire given by this parametric equation with the parameter t going from -2 to 2√3. That defines the wire. Now, in that setup, we needed to compute the arc length of this wire. And we can do so by evaluating this integral. So in this video, we will discuss how we would set up how we'd evaluate this integral. It'll involve a trigonometric substitution. So let's take a look at this. Thinking about this as being 2 squared, and over here this is being t squared. We can think of a triangle. And the hypotenuse is what we see right here, where we have this squared plus this squared. The square rooted would be this. Okay, so then from that triangle, we can also think of a similar triangle where notice we have a constant here, so we can use a triangle to set up with a constant here with secant on this side and tangent on this side. But to make them related, we need to multiply all the sides in this triangle by 2. Okay, and then we know that this part right here is simply 2 secant theta, and we need to figure out what dt is. So dt we can get by thinking of t as being equal to 2 times tangent theta, and then taking the derivative, we'll end up getting this. Okay, and so we can put that in right here, 2 secant squared theta d theta. All right, so then we integrate this, remembering we have t values from -2 to 2√3, and we can use the equation t is equal to 2 tangent theta, and solve for tangent theta, t over 2, and think for a minute that when we want tangent of theta, so at -2, we're going to have it being -1. And what value of theta gives us -1, where we've restricted tangent in this substitution for t so that it's 1 to 1, the normal one for arctangent from -pi_2 to pi_2. And we want to look at where it's equal to -pi_2, and that's going to be precisely at -1. Okay, let's see, when is it equal to -1? It's equal to -1 at -pi_4, sorry. And then from there, where is, so when t is equal to 2√3, we end up getting tangent 3 is equal to square root of 3. That's the steeper slope for tangent as we're heading toward pi_2, or the steeper slope of this radial line, and that'll be happen at the angle of pi_3. So this is our integral right here. Okay, so we're going from there to there, and we have 4 times secant cubed of theta. So let's discuss how we're going to do this. We're going to need an integration by parts to do this one. Now, so we just did trig substitution to get to this far. Now we're going to do integration by parts. Okay. So all right, so let's rewrite this up here. All right, and maybe we can write it as secant theta and secant squared theta as follows. So we can think of an integration by parts because we know how to take the antiderivative of this and the derivative of this. So make a little table. We get antiderivative, derivative, and then we can think, okay, we put a plus and minus. It's going to be, and we have this 4 multiplied out here. So we have 4 times this, it's secant tangent theta, minus, then we're going to have this integral here. This dashed line just means multiply across here. Now, we actually have a repetition here because of an identity that we have. The tangent squared of theta is equal to secant squared theta minus 1. Notice that'll be a repetition in here when we multiply because we're going to get a secant cubed out. And the other part, when we have a -1 times secant, we'll be able to find the integral of that. So we'll work out just fine. We kind of have a repetition at this level. So we stop, we do it through an identity, but then we have something extra to integrate, but it works out. So let's take a look at this. So this is minus this integral secant theta times secant squared theta minus 1 theta. And of course, we have a 4 here. That's going to become minus 4 secant cubed theta when we multiply that through. So remember that we use the identity here for tangent. So we have tangent squared, but that's what tangent squared is. So if we multiply this through distribute, we get a secant cubed, but then we also get a secant, but let's put that in a new integral here because it has a subtraction sign and we can split the integral over that. So and minus becomes a plus here. So plus 4 secant theta. And of course we have this right here. Okay. Now, notice that this is the same thing as this. And this is what we're trying to solve for, right? And so that's equal there. Okay, and we need to put some bounds in everywhere. And so we already took an antiderivative, but when we take an antiderivative with the definite integral, we got to put the evaluating symbols to evaluate and subtract. So these symbols really are everywhere here. Let's keep that in mind. So doing that, we know that this is A. We also know that, okay, well, let's just label this as A. Then we have A over here, and we're trying to find A. Notice that, so we can add this A to the other side and get a 2A is equal to this plus that. So we could divide both sides by 2. So we have 1/2. And let's remember right here, we could actually take an antiderivative of this. It's secant, natural log of secant theta plus tangent theta, and we're going from these bounds here. Now, so we have an antiderivative evaluated, and they're added together. So we could actually pull the evaluation to the far outside and just put these two things together. So we end up getting 4 secant theta tangent theta, and remember we have a 4 here, plus 4 natural log of secant theta plus tangent theta. Okay, and that's evaluated from negative pi fourths up to pi, okay, from pi thirds. Okay, so let's, so this will be, remember what we're calculating, because we did trig substitution, we did integration by parts. We finally get to this step. All right, we've actually taken an derivative. Now we can evaluate. So if we plug this in, we plug in pi thirds for secant. Let's think about what that is for cosine. If we plug in pi thirds, so pi thirds is the angle that's closest to the pi halves. So it's a smaller x value. X value is a half. So secant will actually be 2. Also, maybe we can factor out this 4 actually. See that? We can factor out the 4 and put that with the 1/2. So we have a 2 on the outside. So the 4s are gone. Then secant theta, like we said, is 2. Tangent is actually the slope of this radial line here. It's a steeper slope out of the different slopes. It's √3. And over here we have plus, we already factored the 4 out. So we're plugging in pi thirds, so it's natural log, and we already said what secant and tangent were. So we have 2 plus √3, and it's positive, so we can ignore the absolute values. Okay, now 2 times, and let's just keep the parenthesis on the outside here when we do, and factor the 2 even out of the subtraction here. Minus, we're going to plug in negative pi fourths to all of this. So negative pi fourths, the x value is still positive, or the cosine value is still positive. And then secant is just the reciprocal of it. Cosine is √2/2, which is the same as 1/√2, and the reciprocal is just √2. So secant will be a positive √2. So we get, so here we end up getting, so we have minus this, so 4 is out of the picture. So we have √2, and the tangent negative pi fourths is going to be a -1. Okay. And then we have, minusing this part right here. So minus the natural log. We already put pulled the 4 out and did all that with the 2. So natural log of, then we have, again, square root of 2 and then -1. because -1 for tangent and that. Okay, and like that. Okay, so then this is 2, let me check. 2, and we have square root of 3 times 2, natural log of 2 plus root 3. Plus, and this becomes a plus root 2, and then we have a minus natural log of quantity squared of 2 and -1. So I actually checked this with technology a couple times to make sure this was correct and accurate from different steps here, and that is correct. And as a decimal, which might intuitively make more sense. So the length of this wire in units, unit lengths, depending on what we're thinking of these units as being, inches or something else, it's approximately 14.15 units long. Okay, so that's so we just computed the arc length, and we'll need that in the calculation in the next video. Now we'll actually tackle the integration for the x bar, and we will find the centroid. Thanks for watching.